All right, I guess we'll get rolling here a couple minutes after 11 Mountain Time. So good morning or good afternoon, everyone, and welcome to today's webinar titled Designing and Utilizing Meter Systems for Commissioning and Optimization. This presentation is brought to you by QMC and co-sponsored by the Eastern and Western Canada chapters of the Building Commission Association. My name is Craig Hatch. I'm from the Western Canadian chapter, and I'll be the moderator for today's presentation. Please note that throughout the presentation, all microphones will be muted to minimize any background noise or feedback that may distract from the presentation. We'll be using the Q&A function for questions. So if you have any questions, please submit them through the Q&A function found at the bottom control panel of your screen. You can submit questions anytime and we'll compile them. Throughout the webinar and at the end of the presentation, we'll have time to address and answer your questions. We'll also be recording today's webinar, which will be available to view on the BCA's website. Today's presenters are Pete Sanei and Mike Easton. Peter joined QMC in 2017 and is currently managing the institutional and instrumentation divisions. Peter has over 14 years of combined experience in commercial and high-density residential HVAC systems, along with industrial instrumentation and process automation serving steel and aluminum, food and beverage, and pharmaceutical industries. Peter obtained his BA in process automation from McMaster University. Mike Easton is the Vice President of Sales for QMC Metering Solutions for Eastern Canada. Mike has been a partner with QMC since 2006 and has spent over 10 years focusing on business development in Ontario and Quebec. After opening QMC's Toronto office in 2012, he obtained his BBA from Simon Fraser University in 2002 and is a certified measurement and verification professional. Welcome, Peter and Mike.
Thank you very much, Craig, for the introduction, and thank you to Nicole as well for organizing this. And want to thank everybody for attending and the Building Commissioning Association for this opportunity. Just wanted to quickly touch on the agenda for this afternoon. We're going to very briefly talk about QMC and then talk a bit about why metering systems are critical for building commissioning, as well as continuous optimization. We'll look at some common challenges with meter systems and then show how to best plan and design an optimal meter system. We'll review hardware, communications, and software. And then look into some case studies of what we've done with actionable meter data received from systems we've deployed. And then finish off with a summary of how to design a great meter system and then a question and answer period. We do have a lot of content to cover today, so we're going to move through this pretty quickly. So again, please hold your questions till the end. Just a bit about QMC. We've been in business for 25 years. We service, deploy and service meter systems across Canada and recently expanded to the United States. We work with all different types of metering systems from electrical, thermal, water, and gas, and work with many different meter manufacturers. And every day our system, Meter Connects, it's a cloud-based software, collects over 250,000 meter points, and that can be anything from real-time data to hourly data. So it's a lot of meter data we receive and analyze. And just a bit about our vision, you see propped up behind Peter and myself. We really believe that building energy sustainability can be achieved through good data being made available to various stakeholders, and we really focus on three stakeholder groups. That is tenants. So if they're provided meter data and billing, they are usually financially incentivized to conserve and held accountable for the utilities they consume. Building operators as well, if they're given good meter data, can see when and where they're consuming power with and other utilities within their building and be held accountable to run the building better. And lastly, third-party groups who are supplying equipment or services to the property, this is really around measurement and verification, could be held accountable for the services and products they're deploying by ensuring that good meter data is available to monitor those systems and services. And just what is driving more metering in buildings these days? The first is obviously utilities continue to go up. Water in particular in the last decade is continuing to go up at a very increasing rate, and the need to monitor and manage those utilities continues with that cost increase. There's definitely a bigger push towards smart cities and smart buildings, which all require metering as part of their sensory systems that are deployed within the buildings or the cities. And there's increasingly numbers of standards and accreditations that are requiring metering in them. One of the first big ones we started working with was LEED 2009, LEED version 4, ASHRAE 90.1, and the energy standards set out in that are really enforcing a lot of metering within Canada these days. It's probably the standard we see the most being utilized, and even ISO 50001. And on the regulatory side, we have Measurement Canada that, with the Fairness of the Pump Act, is highly regulated electrical and gas metering. And very recently, Measurement Canada has begun regulating thermal or BTU energy metering. And we'll talk a bit more about that in the discussion today. And what's helping facilitate all this is metering is getting more cost effective as we continue. When I first started with QMC, a typical electrical meter point was around $1,000. Now it's about 400 to 500. So that increasing the lowering of equipment costs is making it easier to supply and deploy meter systems. And why is metering critical to commissioning and building optimization? Well, our old adage, if you don't measure, you can't manage it. If you don't see where your utilities are being utilized and when, then it's very hard to manage them. And we use interval data consumption and demand data to ensure that loads are being utilized properly. And obviously we're identifying anomalies and setting alarms along those systems. And there's even more parameters available in more advanced metering, so you can better judge how systems are working. So we're talking about power quality, pressures, temperatures. All this data is available from good meters and good meter systems. And of equal importance is once you've commissioned the system, you make sure everything's running. I like the adage that low-hanging fruit grows back. You can obviously find those anomalies with systems, but you need to keep on top of it, because a year or two down the road, those the inefficiencies in systems can come back, and you want a good meter system to catch that. And this is just a clip that I got out of an ASHRAE publication quite a few years ago, and just shows the savings that can be achieved with a meter system in place. I actually argue that their billing allocation savings of 2.5 to 5% are actually a bit low. We've seen some commercial and especially residential tenants save over 30% once they're actually billed for their consumption. But the building tune-up and ongoing commissioning are obviously critical. They need meter data to see when and where utilities are being used, and if changes made to those systems are implemented, what kind of savings you get. So again, metering can really assist in the tune-up and the ongoing commissioning process. And that's probably what led ASHRAE to really implement a lot of metering in their more recent designs. So here are some challenges that we've come across in our history with metering systems. First biggest challenge is proprietary meter hardware being deployed. So a manufacturer supplies and installs a system that really only they can read. And obviously that really limits the ability for the operations team or any other third parties to access that meter data and do good things with it. So our solution there is always deploy systems that have open protocols. Examples of BACnet, Modbus, TCP/IP, etc. are the way to design systems moving forward. A great meter can be installed, but if it's not checked that the installer installed it properly, it might be giving you erroneous reads. And actually, we find most of the time it is. So it's imperative that a meter is installed and inspected, whether that's by the manufacturer, a regulatory body, or a commissioning agent, to ensure that the system's installed properly and communicating data back properly. And typically, we look at three levels of commissioning. We want to look at the meter installation itself. We want to look at the communications from the meter to some type of data collection system. And then lastly, we want to verify that it was programmed into the software correctly, so that multipliers and other parameters are inputted correctly in the system and given accurate reads. Poor data or no access to data. We've seen lots of meter systems deployed where the people who need the data cannot get it. One of our first lead M&D projects we did in about 2010, we were dealing with a lead consultant who said they've deployed 10 systems and still haven't seen any meter data from them. And one of the challenges was they were continually relying on the building automation system to collect that meter data. And it's often a low priority to get that as opposed to setting up the HVAC systems and other things on the control system. So we've really suggested that our systems are deployed with a cloud-based solution so that once the meter system is set up and an organization is responsible for collecting that data online, it's then available to any party who wants to receive it. Stranded meter assets, this is really to do with retrofit projects where you've got existing metering in place and now you want to do something with that metering. We really do encourage integrating with existing meters because they might be it's much easier and more cost effective to integrate with those meters than replace them. There's historically been a disconnect between electrical and mechanical systems being deployed. One thing that happens is a lot of electrical metering was being put into buildings and very few gas or water or thermal meters. So that imbalances the problem, but also those systems often operate on completely different control systems or data collection systems. So you have to go to one system to get the electrical metering, another to get the gas, another to get the water, and maybe even a fourth to get the BTU metering data. And so we really try to encourage all the parties we work with to align the electrical and mechanical systems into one meter system. And then lastly, systems not being regulatory compliant or up to code. So we've had water meters get installed that don't meet safe drinking standards, NSF 61, and need to get pulled out. We've had meters be put in place for billing that are not revenue grade. They need to get removed. So again, you need to ensure that any system you're putting in place is going to meet the regulations and codes of the region they're being deployed in. And before we get on how to design the system, one really important thing to remember about a meter is the majority of them that are deployed in the field are cash registers. They are there primarily to exchange, to be the medium of exchange of a utility between the provider, like a local utility, and the customer, whether it's a building or a sub-metered tenant. And so the requirement primarily is for billing. And then we obviously want to use that same data for energy management commissioning purposes as well. And there's a whole other group of meters that are for energy management only, which don't have the same restrictions on them as revenue grade systems do. So what are our key goals, key ways of designing a meter system? First thing we do is we really sit down with all the stakeholders involved and develop a meter plan. And that's everybody from the engineering team all the way to the end users. So you can ensure that all the groups involved have a say in what type of loads they need metered, what type of data they need from those loads, where they want to see the data, and what they want to do with that data in the end. And with that, you can then design a system that's actually going to meet everybody's needs. We've had lots of systems get put in place where meters were just put in and were needed for billing as an example. They didn't meet that requirement and again had to be pulled out. So that was an example of all the stakeholders not being involved in the decision process. And then we look at these three components: meter hardware itself, communications infrastructure, and reporting systems. And if you don't have all three of those components mapped out before the system is designed, specified, and deployed, it's going to be an incomplete meter system. You're going to have hardware installed that is not reporting, or you're going to have a nice software platform, nice meter hardware without a way of getting data from the hardware to the software, hence the communications requirements. And we do recommend that a qualified systems provider is involved, whether that's a commissioning agency, a meter manufacturer, or another group who can put the whole thing together and ensure that, that all three of those components are working well. This is just a high-level example of those three components on a campus scenario. And you'll see here that there's a variety of different ways we look at the meter hardware, from existing meters in place to new meters that need to be added to meet the current needs of the property, and a variety of different communications options. We're showing up on this complex A, a wireless or cellular solution, hardwired solutions for these two bottom properties. And then, as I mentioned, a software component where all that data needs to go to, and then you're able to do all of the different services and analytics required from that platform, everything from benchmarking and alarming to billing. And really critical here is this API to other energy management systems. If you're collecting data on a web-based platform, it should be made, that data needs to be made available to other groups, because if the system is going to function properly for 10, 20, 30 years, you're going to need to share that data at various points to other parties, whether it's, I believe Copper Tree presented a few weeks ago on this, to this group, their example of fault detection company that would utilize this meter data to do their job better. Hence, that data needs to be made available to groups like that. Just a quick touch on a few different meter technologies in the market right now. I'm going to actually get a little bit more into multi-meter point technology because it's a technology that's used in most buildings now, but not fully well understood. These cellular socket meters are a great meter for metering dispersed loads where you have old glass meters. You pull that out and put a new cellular enabled meter in, and that's immediately communicating to the cloud without any advanced infrastructure needed on site. And same with this cellular enabled water meter where you have dispersed water meter requirements such as irrigation, perhaps a few large tenants like a restaurant or a gym within a building. You're able to put these devices in and get 20 years of battery life out of communications without having to hardwire a solution. And lastly, just touching on BTU metering as well. Pete's going to talk about that in a few slides, and we wanted to touch on it because Measurement Canada is now regulating this technology, and it's much more prevalent in new buildings lately. Apparently, there we go. So this just wanted to go a little bit further here on these multi-point meters because they are so common in commercial, institutional, and multi-res properties these days. This shows 8 breakers or 8 loads on a distribution panel where we've put current transformers on the A, B, and C phase of each load. But what this allows you to do is monitor 8 meter points or up to 24 current transformers on one electrical meter. And that allows for massive cost savings, easier installations, and you're getting a ton of data out of these systems in the end. You can do everything from 100 amp solid core CTs all the way up to 5,000 amp split core CTs. Quick note on split core CTs, those are only for information purposes. You cannot use those for billing applications within Canada. And last point here, we do want to get that data out of these meters in an open protocol, non-proprietary fashion. So whether you're sending that to a cloud-based system or you're communicating BACnet IP to the BAS, it's an important requirement of any meter to have that flexible communications out. Pete, would you like to take on BTU metering, please?
Sure. Thanks, Mike. As Mike mentioned, we wanted to emphasize on BTU metering a little bit more as it's a newly regulated commodity. There's a lot of misunderstanding around the subject. So we wanted to go a little bit more in details about thermal meters. Thermal meters, as most of you are familiar with, use 3 main components to calculate thermal energy: a flow meter measuring liquid volume, a matched pair of temperature sensors measuring temperature difference between the beginning of the load or supply and the end of the load or return, and a calculator. Next slide, please. I wanted to go over thermal energy calculation as some of the larger energy consuming systems within the buildings are central hydronic HVAC system and the domestic hot water system, whether it's used for billing or rate setting or energy management. Accurate metering and data is necessity. In the equation shown here, density and specific heat capacity of the temperature are dependent factors dependent factors on the temperature where the measurement is taken. Where BAS systems take volume and temperatures from flow meters and temperature sensors and typically use a constant factor to calculate energy, thermal meters take density and specific heat capacity of the liquid at the measurement point to do this calculation using a constant factor throughout the operating range of, let's say, 5 to 75 degrees C in a hydronic system could result in somewhere between 3 to 5% additional uncertainty in the reported energy value. Typically, an energy management system or a BAS system uses a constant factor as opposed to using the calculated factor to calculate the thermal energy. Next slide, please. So we categorize thermal meters in three main groups, broken into four categories. Inline thermal meters, which are the only type that can be used for revenue or cost sharing applications, typically offering a better measurement accuracy and lower maintenance requirements, specifically in the flow where the flow component is a non-mechanical type, meaning having no moving parts. A subcategory of the inline thermometers would be the compact type, typically used for installation within residential fan coils or heat pumps, shown on the bottom left, as the installation space is very limited. With this type of meter, temperature sensor is usually immersed within the body of the flow meter, and calculator is mounted on top of the flow meter, offering a very compact solution for energy measurement. On the top right, insertion type meters which could usually be used for energy management applications, offering significant cost savings when it comes to larger pipe sizes, around 8 inches or more. This type of meter typically can be hot tapped and installed without any interruption or shutdown within the system. However, we need to keep in mind that periodic maintenance is necessary for accurate measurement of this type of meters. And then clamp-on meters, which are suitable for temporary installations and energy audits or validation of other types of meters, offering lower accuracy due to additional uncertainties such as pipe thickness and so on. But advantageous in the sense that they could be installed seamlessly on the outer surface of the pipes. Next slide, please. I also wanted to go over the importance of periodic maintenance of the metering equipment, regardless of them being used for cost recovery or billing or energy management purposes. I really want to single out the mechanical meters, such as the positive displacement type meters or the impeller type meters commonly used on the domestic water applications, or the insertion turbine type meters used for flow measurement in thermal energy calculations. Hard water or untreated liquid within the hydronic loops typically degrade the accuracy of these meters, causing them to slow down or reporting lower volumes. So it's very important to validate the accuracy of these meters periodically. We typically suggest every 1 to 2 years. Next slide, please. Some of the communication options available from the metering systems range from analog outputs 0 to 5 volts, 0 to 10 volts, 4 to 20 milliamp or pulses, currently utilized typically for control purposes, to digital outputs from Modbus and BACnet and MBus or meter bus, which is standard for sub-metering or billing application these days. Communications along with encoded outputs from some of the billing grade meters, mainly water meters. Wireless communication options are gaining popularity as they're becoming cheaper and more accessible, and they offer lower deployment cost and the flexibility to be utilized in existing properties, not just new construction. We always typically prefer digital communications as we can extract more data or value out of the meters. Next slide, please. For the front-end metering system, some of the reporting options include web-based energy management information system, softwares or data warehouses, or building automation systems, intelligent building master systems, remote billing platforms, and on-site PCs. However, as Mike touched on earlier, cloud-based softwares are gaining momentum as they offer more flexibility when it comes to customizable remote access for multiple stakeholders, such as billing companies, energy managers, and facility operators. Next slide, please. So to us, at QMC as a metering solution provider, a complete turnkey solution starts from assessment for efficient design, hardware installation, installation verification, integration in some sort of a data collection system and software, a complete system commissioning, training the stakeholders, and documentation, and a good maintenance plan at the closing stage. Next slide, please. Over to Mike.
Great. Yeah, just one last point here on training. I wanted to extend on, you can put the best meter system you want in the world, and if nobody knows how to access the data and use that data, it's not going to get the results for it. So we really do stress training, not just once the system's deployed, but every the first 6 and 12 months, do a follow-up with the team using the system to make sure they're utilizing all of the features available to them. We find that after training, only about a third of the people through training use the system. So we do try and come back again and ensure that they're using it to its full potential. So just we wanted to show some software samples here of what you can expect to do with the data once you receive it from the meter hardware deployment and have a communication system in place. We're going to show some examples of utilizing a web-based solution, but this would also, a lot of these same functions are available on site-based solutions or within the BAS. So one of the things we like to do with meter data, especially building level meter data where we're integrating with the main meters, is portfolio benchmarking. You're able to look at your entire portfolio, see their entire building consumption of electrical, gas, water, and you're able to do a very quick variance report. You can also compare these buildings on their energy use intensities. And if you want more detail on any specific building, it's great if you can drill into that building further. This is a sample of, I believe it was building 1 here, where you go in and can see the consumption of these different loads at a building level. You're able to see if there's an increase in their consumption or decrease, not only month over month, but also the same month of previous year. And as you can see on the right side here, some of the critical loads within the building are also shown. And if there's a variance in their consumption, you're able to see an increase or decrease there. Fully automated reports can also be sent showing every meter point within a property and their plus or minus variance over a week or a month or any period you choose. And drilling in further, even any meter, this is where you can really see the power of interval data. This is an example of a thermal meter on a heating loop, what we're showing here is the interval data for about a 7-8 month period. You can see a lot of information here, for obviously the orange being the total consumption of that meter over this period. We've set, in this case, a threshold of 150 kilowatts to trigger an alarm if the consumption of the meter ever hits that point. And you can also see in the background here, heating and cool or degree days over 0 degrees, and in light blue, days that are under 0 degrees. So you can see that correlation of heating use versus weather right in one spot. And if you're getting instantaneous data, you're able to see the most recent parameters in supply flow, supply temperature, return temperature, and flow temperature. Again, if you have a good meter connection, you're getting that extra data, not just consumption data. This is an example at the same level of an electrical meter. We zoomed in a little bit closer here to a 1 week period. Again, you're seeing that weather overlay. This gray line is reflecting power factor, and you can see real-time amperage and voltage of the system and power factor below as well. So again, if you've set up the meter system correctly to pull all that data back into a more advanced system, you can do a lot of analysis of your loads from one spot. So you can ensure that your voltages, an example, are where they're supposed to be. Again, these ones are running what seems to be a little bit high. And this is an example of a heat map, one of our favorite tools to utilize to have a quick snapshot of a load over a 1 month, 1 year period. What have you. This is showing hourly data for every day. Sometimes you can get down to 5 or 15 minute intervals, but you can obviously see the trends of this load very clearly shown when it's hitting its maximum energy use. And you can look for schedule offsets, evening, weekend offsets, and see any anomalies very quickly utilizing heat maps. And this is an example of utilizing the last 7 days to generate an acceptable threshold for any given load. So the light blue area here is showing what the range has been over the last several days. I believe what we've done in this sense is use the last 7 of the same day, so 7 Tuesdays as an example, and you want to see that your consumption is within there. You'd also see a best day that you could be targeting towards, and again, adjust not only this can be at a building level, this can be at a piece of equipment, this can be for an entire floor, and you can take actions to actually get towards your energy objectives using this data. And everybody's favorite, regression models. So again, a good software should allow you to generate regression models and look for a correlation between a load's consumption versus a heating and cooling degree days, as an example. You can also put in other factors like occupancy, which has had quite a change due to COVID lately. So those have been some interesting graphs we've been looking at there. And lastly, load comparisons are very important. The ability to overlay the same load against itself over several weeks, or look at several of the same load or same type of load and how they compare. In this case, we've got the electrical panels of 10 different floors and seeing how they're comparing to each other over, this is just a 1-day period. So you can see not only the energy profile of each one, but again, how they vary. And you can turn that into a quick comparison using pi or other types of charts to see where you have extensively more use in the same type of load, and obviously act accordingly. So I wanted to take a look at a few examples here of specific case studies we've done. This is one of my favorites. It was one of the first ones I did with a lead project where we were working with an M&D consultant, and they deployed our meter system, and we're looking at the data and seeing that the consumption in this building was not matching what the modeling had done. So we worked with them to develop a graph after a few months, and showed that this air handling unit was essentially running at full tilt 24/7. And you can see through this heat map was using a lot of energy over this period. They took action and quickly set the schedule to where it needed to be. So you can see the on-off times very clearly here, as well as the system turning off pretty much completely over the weekend. And then by this point in January, they'd actually optimized the settings of the air handling unit to be at the correct temperatures and settings, so it was using less energy during that time. So back to this kind of yellow or medium setting of energy consumption. And then a few months later, it was manually overridden, and you can see that happening here, going back to a scheduled settings and then back to manual override. So it was neat to see how the design of this system was impacted by manual interference throughout the operation of the building over a 1-year period, and obviously impacted their ability to hit their energy targets. This is another example of a building, a lead project where we were metering. It's very typical for lead projects to have a total consumption on an office tower floor and break that into lighting, plug load, and mechanical loads. And so we noticed a few floors were operating not within their expected range, as shown by this profile here. There was early starts and higher peaks near the end of the office day. And so we utilized the multiple meter points on that floor to do a bit of load disaggregation. You can see here in the red the total load. You can see that the plug load's pretty consistent throughout the day in blue. Lighting comes on during pretty much operating hours. That's great. And it was really the heat pumps that were set to turn on very early here, which they adjusted to a later setting as well. We're also turning on late in the day as people were leaving. So that was corrected, and you can see that it was really the culprit in the extra energy use within that floor. Pete, I'm going to hand it back to you to go over this example.
So this example is showcasing a cool case study utilizing thermal metering data to analyze fault within a residential fan coil. The graph in the middle shows supply temperature in red, return temperature in blue, and thermal energy demand in orange from the thermal meter within the fan coil. And the graph on the bottom shows simultaneous demand from the hydrometer for the same suite. The occupant in this suite was complaining about heating issues, and looking at the meter data and the graphs in the middle, we could easily diagnose the cause as a stuck actuated control valve, which is a common occurrence in residential fan coils and heat pumps. As you can note from the supply and return temperature in red and blue, in the beginning of January till the 27th, where the service tech was dispatched to site, both temperature sensors are measuring near ambient temperature around 20 degrees C within the suite, with near 0 delta T as the control valve or the actuator is stuck in closed position, and the fan coil, the fan within, or the air handler or the fan within the fan coil is operating constantly using electricity without the ability to satisfy the set temperature on the thermostat. As soon as the control valve and the actuator get serviced on the 27th, the supply and return temperatures go back to normal near 70 degrees C, and the electricity consumption drops as the fan within the fan coil goes back to normal operation. Next slide, please. This is another cool case study. We have rolled out leak detection within our water metering portfolio. This is representing the water consumption within a residential suite. The blue lines are representative of the volume through the cold water meter, and the red lines, which are not really visible on the bottom, represent the warm water consumption within the suite. As you can see, this was diagnosed later on, was pinpointed as a leak within the suite, and was identified as a leaky toilet flush that was getting worse over a certain period of time. And when we looked back from the time that the leak started, it had wasted somewhere around 100 cubic meters of water within this period. And looking over the previous period within the same building, we revealed that there were 5 other units with similar issue, with similar amounts of leak. And when we converted it into a dollar value, it added up to over $11,000 of wasted water. Our data collection software is currently identifying any continuous consumption from the water meters within a given period of time, which is, we deem that for 24 hours as a leak, and we sent notifications to either tenant or the property management or the billing company. Next slide, please. And I mentioned earlier, we preferred digital communications from the meters, as they would offer more value and more variables out of each meter. One of the common issues when it comes to thermal metering, where most of the flow meters are using 24 volts power from supplied either by a transformer within the fan coil, or transformer that is installed separately serving the meter. We're seeing a lot of errors here as power disruption for the flow meter part of the thermal meter. And this is shown here as communication error, or the supply voltage interruption. The meter at this point, when there's no power provided for the flow meter to make the measurement, there would be no energy recorded on the calculator. Also, one of the other common issues within the hydronic loops is interrupt air bubbles. which causes erroneous readings from the ultrasonic type flow meters and thermal meters. And, you know, this is one of the other things that could be extracted from the meters as within the error logs, alongside with supply and return temperature and flow and energy and demand. And this needs to be addressed. We typically notify the building operators that there is excess air within the loop, and they need to rectify the issue. Next slide, please. So, Mike, I'll pass it on to you.
Yeah, great. Thanks, Pete. So yeah, that's our last slide. We just wanted to summarize. So when you're designing a good meter system, look for including all of your users and stakeholders in the design process. Ensure that all of the systems that you're designing do meet Measurement Canada requirements if it is for billing, or other local standards such as safe drinking water codes for water meters. Include all 3 levels in your system design: hardware, communications, and software. Without addressing all 3 of those components, you will not have a complete meter system. Do ensure open protocols and non-proprietary equipment so any group can access that meter data. Verification of the systems is critical so that you're 100% assured that the meter reads you're getting are accurate, the installation is done correctly, and verify and ensure training is done so that people who are going to utilize the system know what they're doing with the system and come back and use it regularly. And lastly, please do utilize these systems in the end for energy management or billing purposes. We've seen too many meter systems get deployed and not be used to their full potential. So they're just not getting the sustainable savings that we're looking for from these systems once deployed. So ensure that the groups who are tasked with using them are using their full potential. At this point, we'd like to take some questions and hopefully give you some great answers.
All right, thanks, Peter. Mike, as you said, we'll jump to the few questions we've received. Keep your guys, anyone have questions, keep them coming. And so first question, probably Peter. Can you give the idea of cost difference between the 4 types of BTU meters that you've shown in your presentation?
Sure. So inline meters, with larger inline meters, it would be highly dependent on the pipe size and the size of the meter. And these meters would cost from anywhere ranging from starting from 1 inch, ranging from $600-700 and going all the way up to, 20-inch and 24-inch lines in and around $20,000 to $25,000. The compact meters, depending on whether they're revenue grade and approved and where they're made, they range anywhere between $200 to $250 to about $500 to $550. Typical sizes are between 1/2 inch and 3/4 inch. Insertion type meters, one of the most popular ones that are currently used are the Onicon ones, which, depending on whether they're using a turbine type or impeller type insertion flow meter or a magnetic type flow meter, range anywhere between about $3,500 to about $6,000. And clamp-on meters, depending on the manufacturer, clamp-on thermal meters, depending on the manufacturer, for a complete package, including temperature sensors and clamp-on ultrasonic sensors, cost anywhere starting from about $4,500 to about $10,000.
And just a clarification, those are products supplied, not installed, correct?
These are just the hardware costs, correct?
Okay. Someone's asked a question. This isn't necessarily for you guys. Recording will be available on the BCA website later. So if you've missed the beginning of the presentation, sorry, but you'll be able to download this at a later date. Few questions on are the slides available? You guys want to receive emails requesting, or?
Yeah, we were going to make a PDF of this available at the end of the meeting for everybody.
Okay. Not seeing too many other questions. I guess everyone either knows about meters or you've covered all your bases pretty well.
Excellent. Well, I do see a few Q&A up at the top. Were those just point of order about? Yeah, there was a question here about was the meter cost installed or product cost? What we would use as a general rule of thumb for the numbers that Peter provided on these meters, you probably use a percentage of about 60 to 80% of their material costs you could look for in the labor cost. So if you suggest it's a $5,000 meter, it's probably a $3,000 to $4,000 install. Pete, is that a safe figure you'd agree with?
With the exception of clamp-on meters, which typically offer a much lower installation cost as they get installed on the surface of the pipe. There was one last question. Do you have anything regarding airflow? Yes. So we typically use mass flow meters, thermal mass flow meters for airflow measurement, typically in forced air applications. We use insertion type for either duct, round or rectangular duct measurement.
Sorry, Peter, and there's just one just popped in. How do you meter plug loads?
Yeah, so typically we would, for whether in a typical commercial application, we would look at utilizing one of these multimeter systems for metering plug loads, where you would go into a distribution panel, and whether they're 15 amp, 30 amp, or 60 amp breakers that are feeding a variety of different plug loads within the office floor, as an example, you would use current transformers for that. And when I was mentioning you get a very low cost per meter point, it's when you're starting to utilize these multimeter technologies, because the cost of the CTs are very minimal, like $15, $20, and then you're utilizing 1 meter head essentially for up to 24 CTs. There's other manufacturers that actually do up to 40 CTs or even 100 CTs on some devices. You get a very low cost per meter point when you do that. And at the same time you're metering plug loads, you're also able to monitor other loads within that distribution panel.
So obviously, historically, it depends on how the electrical panel is laid out. If there's a circuit that feeds plugs and lights and a bunch of general stuff, then obviously it's not going to be plug load, but.
Correct. And there's another trick a few tricks you can utilize with this kind of technology. You can also use one set of CTs to monitor the entire panel. And then let's say you meter a few lighting loads and a few HVAC loads. You can then use software to take the entire panel's consumption, deduct lighting, deduct HVAC, and that leaves you with plug loads. Another trick is you have multiple little circuits that are feeding a variety of loads, and you don't really care if you isolate each of those. You can run multiple circuits through the same CT. I mean, let's say you have 8 A-phase loads that are all going to small plug loads. You can run them all through the same CT, and it'll just totalize those for you. Again, saving on your hardware and installation costs in doing that. One thing I had to kind of trim out of our presentation today, though, was doing the correct amount of metering. We find a lot of buildings these days are moving toward metering everything. And as much as that's great for the metering industry, sometimes it's metering overkill, where they're metering every circuit. And before even entire floors are metered or other utilities are metered properly, like you're missing, the entire water irrigation system, but you're metering toaster loads, right? Like, we really believe in that balance of metering large loads first before you get down to metering individual plug loads or individual lighting circuits, as an example. I saw a few other questions come in. Craig, are those?
Yeah, so are the CTs are analog sensors, or are they a special type of CT? Is a question that's just asked.
Typically, the types of CTs we use are revenue grade type approved, and they're what's referred to as an 80 milliamp output or a 5 amp output. and those connect back into the meter themselves. They're not an analog output.
Do you guys utilize split core or are they solid core?
The majority of the time, probably 90% of our deployments are solid core CTs for a few reasons. Three reasons. One is any billing application, it needs to be a solid core CT. The solid core CTs are usually less expensive. So for new construction applications, it's usually cheaper to use them anyways, because you don't need that split core technology for a retrofit. And lastly, they are more accurate. So it's typically best to use solid core when possible, but split core you need to utilize often, especially in retrofit applications where you're dealing with bus bar or larger cables, or a load that can't be shut down for more than a few minutes, in which case you can go and put the split core CT on and then re-energize the power. There's not very many contractors anymore who want to do live CT installations with split core CTs, so you usually still need to shut down.
Actually, a question: what percentage of your projects are installed for revenue grade, like seeking payback or billing to clients?
Well, we do a lot of multi-res projects as well, so that skews our percentage to upwards of 90%. If I remove multi-res and we just focus on our institutional clientele and commercial, it would probably be 60%, probably 50-50. Pete, you happy with that assessment? Yeah.
Yes.
And if someone's, sorry,
I mentioned there was like the ASHRAE standard. We're seeing that a lot more these days in the design. So that level of metering for ASHRAE is very similar to the old LEED 2009 standard, where there was a lot of metering, especially electrical metering. And so that's driving a lot more energy management metering these days.
Sorry, if someone is seeking revenue grade, how often do they need to be looked at on a yearly basis, like from a calibration standpoint, or once they're Measurement Canada approved, they're good for life?
Yeah, great question. So any Measurement Canada approved meter is given a seal period, and it's stated by Measurement Canada. So most electrical meters have a 10-year seal period. So once it's installed and commissioned, you just need to remove it every 10 years and retest it. And usually when you reinstall it, it's given a slightly longer seal period the second time around, like say 8 years. If you have a substantial amount of the same meter deployed, you can look at sample testing. And then for gas metering, it's typically a 10-year period. And with the thermal metering, as is relatively newly regulated by Measurement Canada, they haven't come out fully with the terms of the seal period, but it's probably going to be somewhere between 6 to 10 years. Just to elaborate on water, water is not regulated by Measurement Canada, but it is utilized by so many utilities across Canada. Typically, we recommend that water meters are replaced every 10 to 12 years, but they're usually fairly reliable piece of equipment and should hold their accuracy for almost a decade.
Very good. Well, if there's not any other questions, I guess we can wrap it up. So thanks again to Peter, Mike, and QMC. We appreciate your time and expertise. If you have any follow-up questions, please reach out to either the BCA or Mike's going to put their email addresses back up on the screen here, and you can contact them directly. Again, on behalf of the BCA, I'd like to thank everyone for attending today's presentation and hope you have a great day.
Yeah, thanks. Thank you, Craig and Nicole, again for setting this up, and thanks everybody for participating. I apologize, I missed our contact details there. Mike at Q Meters, Peter at Q Meters.
Thank you. Thanks, everyone. Have a great day.